Another way to make macroscopic superpositions disappear, which is Bohmian mechanics. Or de Broglie-Bohm theory. Okay, so this, I think there is sometimes, I mean, not for such an educated audience, but usually there is a misconception that this theory is sort of falsified or doesn't work with Bell's theorem, or that it's not possible. So let's quote Bell on this as a starter, as a argument that it's interesting to look at Bohmian mechanics. So this is from Brickmont's book, chapter 5. But this is in an article of Bell that I don't remember which it is, probably in Unspeakable and Unspeakable. So Bell says, Bohm's 1952 papers on quantum mechanics were for me a revelation. The elimination of indeterminism was very striking, but more important, it seemed to me, was the elimination of any need for a vague division of the world into system on the one hand and apparatus or observer on the other. I have always felt since that people who have not grasped the idea of those papers, and unfortunately they remain the majority, are handicapped in any discussion of the meaning of quantum mechanics. Why is the pilot wave picture ignored in textbooks? Should it not be taught not as the only way, but as an antidote to the prevailing complacency, to show that vagueness, subjectivity, and indeterminism are not forced on us by experimental facts, but by deliberate theoretical choice? Okay, so I think this is a good introduction, because this is sort of what we want. We are not going to think it's necessarily the final answer, but it's probably a great example of a theory that makes sense of all the predictions of quantum mechanics in a very different way from what we are usually taught. It's a very simple theory to define, but it's very subtle to interpret, so to understand how measurements work in this theory. So that's why we'll have to be careful. But so okay, it's a bit more subtle than what meets the eyes first, and that's why some people sometimes make calculations too quick and conclude the predictions are not correct in comparison with quantum theory, but we know that's not true. Okay? What I will say later is that ultimately all the predictions we know of Copenhagen quantum mechanics can be re-derived within Bohmian mechanics, but not necessarily trivially. Okay, so dynamics. What are the dynamics of this theory? So I start just like for collapse models. Again, psi obeys the Schrödinger equation. Always. There is no measurement, no nothing. So it's IH bar dt psi. And here, H psi, H is going to be the n particle Hamiltonian. So here I really want to take right away an n particle Hamiltonian. Okay, I realize I didn't. Let me just not put the arguments here so that this equality is correct. Very well, so that we know this is standard, but again, no measurement postulate. And now, the positions of the particles also have equations. So they are called, if you want, Q1, Qn. It's an n particle system. Each Q is a vector in R3. They obey the differential equation dqk of t equals v psi k of Q1 course, this is a tautology in a way. Okay, the particles move according to some vector field, and this vector field is given as a function, is given from the wave function. And that's it. Okay, so sometimes I think Detlef Dürr had a nice way of summarizing what's the picture of the world in Bohmian mechanics. Particles move. Okay, there are particles, they exist and they move. That's the take in Bohmian mechanics. And just the way they move is given by this vector field, this velocity field. All right, so this is the extra piece from Bohmian mechanics. So some comments. So this, I put dots here because I mean it as a scalar product, so it also works for spin. So for example, when I do something like this, what I mean is something of for example, okay, so spin is taken into account in this equation, but spin is not a variable like position, like I don't know how to write it. It's not a property of Q. So if you have extra degrees of freedom, the particles, they remain bare. Okay, like spin is a property of the dynamics. It's not a property of the points anymore. Okay, maybe another comment is that in almost all situations that are simple, it is well defined and deterministic. So particle deterministic. So it's not a nil-defined theory in the first place. It's a perfectly fine model. If you give an initial wave function and initial particle configurations, this is something you can evolve forward in time as a Cauchy problem. Okay, last comment. It can be realized experimentally with droplets, experimentally with droplets on oil, oil droplets interacting with their own wave. But this is just single particle. And so it's a bit misleading. So it's the experimental realizations that are kind of neat, when they realize effective Bohmian mechanics with effective Bohmian mechanics analogs, with macroscopic systems. But there are systems in which the wave function lives in real space. So it's like the wave function on physical space, non-configuration space. So there is no non-locality, for example, just single particles. So a bit trivial, at least as far as foundations are concerned. Doesn't tell us much about the world that these examples exist, although they are cute. Okay.
So essentially, you can only understand like Jung's double slit experiments.
So double slit experiment can be done,
yeah, but
you couldn't do like EPR stuff. Right. Yeah. And I disagree that everything is in the double slit experiment. Like to see the weirdness of quantum mechanics, you really need EPR type scenarios. Okay. question, where is this V K psi coming from?
Sorry, what can you maybe be more precise about what can you realize experimentally? What do you mean?
This is maybe a comment because many people have heard of Bohmian mechanics from experimental realization, say of Yves Couder with droplet bouncing. I'm just saying these are neat and cute, but they miss a crucial subtlety, which is that they work only in the single particle case where configuration space is equal to physical space, and where the wave function is a wave in real space. But the subtleties of quantum mechanics come when the wave function is at least in a non-trivial configuration space, and that's where you get like EPR or Bell-type non-locality. And certainly you cannot get these with these experiments. So they are a nice illustration that this is not a crazy dynamics, but they are not, they don't get the full quantumness, and so I don't think we should go too far, in saying how much they tell us about quantum mechanics as an analog. It's sometimes seen as a very nice feature that they have this practical analog, and I don't think that's such a strong point in favor of Bohm. Okay, so really, where is this coming from? What? Yeah.
Just to be clear, so the equation for psi is completely independent of the position of the particle?
Yes, exactly. So the wave function evolves independently, and the particles depend on the wave function, but not the other way around. Yeah. At least at the level of the wave function of the universe. And when you look at subsystems, actually, we'll see later, there is an effective collapse that depends on the particle position. But at least this is, in principle, when I'm writing psi, I'm trying to be consistent, but I realize I'm not. But trying to write a big psi like this for the wave function of the universe, and later I'll try to be a smaller psi. But I realize here already I dropped it. So this is supposed to be for the universe, or at least something big within the universe that includes your measurement apparatus and is not just a small system you're measuring.
Sorry, I think I misunderstood what you just said.
Yeah.
The V is Q1, Q independent thematic position, right?
So V is a field everywhere in space, and it's taken by taking the whole wave function and evaluate it at the coordinates that are the particle positions. So later on, so this wave function here, I will write, if you like, psi of x1, xn. These are the dummy variables of the wave function, and q are actual configuration. Okay, actually, this is poorly so this is correct, but really, this is q1 of t here. So it's the wave function evaluated at the current positions of the particle. Right?
Okay. But so in the pilot wave thing, the wave function can it be complex, for example? Is it just
okay. I shouldn't have mentioned this. I realized. Okay, there are many approximations. It's an analog. Okay. That's also why pilot wave can make it seem a bit. Just the word pilot wave can make it seem a little more simple than it is, because again, it's not usually a wave in real space. It's a wave in configuration space. Okay, we usually don't call waves things in configuration space. Okay, so the big question is, why did I choose this? I mean, I didn't choose it, but why did De Broglie or Bohm choose this? And what does it do for us? This choice, it's not the only one, but sort of the simplest one, that ensures that if the Bohm rule is true initially, then it's true at all time. This evolution is going to preserve the Bohm rule. So if the original Q1, Qn are sampled according to the Bohm rule, then later on, the Bohm rule is transported. Okay, their probability at all times are going to be given by psi squared. So this is something I wanted to show in detail, because it's like one of the few mathematical results there are about Bohmian mechanics. It's a simple result. And so my point is about here is, this is a deterministic theory. There is no randomness in it. And I'd like to explain how we recover the Bohm rule. And there are two steps, more or less, that I have to sketch a bit quick. The first part of the argument is what's often called equivariance. And it's also the intuition about how you find this V psi. What time is it? Okay. And so to find the property of equivalence, what we do is that we compute the derivative of the particle density as a function of time. Okay, so this is the quantum mechanical particle density. I'd like to see how it evolves as a function of time. I'm back to orthodox quantum mechanics here. I would like to look at this, how it evolves as a function of time, because my objective is to write a continuity equation, to write this as the divergence of something. And this would tell me that there is a probability current associated to this density. Okay, and this is, I just brute force. Okay, this is d psi star over dt psi plus d psi over dt psi. I inject the Schrödinger equation in it to get d psi over dt. So these are partial derivatives. This is the sum over j of minus I over 2 mj. Why did I? No, I will keep k. mk of Laplacian k psi star psi minus Laplacian k psi psi star. And then you have plus I v psi star psi minus v psi star psi. Okay, so the potential term cancels. Only this part stays. And that what you can notice is that this is just sum over k of minus I over 2mk of the divergence on the k variable of grad j psi star. Sorry, so move it slow, psi minus, sorry, these are k. So we are kind of almost there. So we can introduce a probability current, Jk. So I define this probability current just from what I have, basically 1 over mk, imaginary part of psi star. And then what we have is that we have the continuity equation. Okay, I was a good person. I kept the sum. And so this is a continuity, a standard continuity equation. Again, independent of Bohmian mechanics. Well, and you realize that from this continuity equation, the probability J is interpreted as the probability current for particles. And so I can artificially write this probability current as the velocity times the density. And so I can finally say that d psi square over dt plus sum over k grad k sorry, this is the divergence of okay, so I can just, this is like a new notation, and indeed this this is how this field I introduced here, I just said it was the right idea, is exactly the velocity field in the continuity equation. Okay. Equals 0, sorry. Yeah. So Bohmian mechanics is just a theory where you decide that the particles are going to flow along the probability current in the way they would in a... So Qj just flows with the natural probability current. Okay, let me now, this is in fact intuitively already done. This is why you guess that you should take V, this choice for V psi. And so now a theorem, maybe it's a bit too much to call it a theorem, but if the bound rule is true at t equals 0, then it is true for all t. I will maybe sharper, yeah.
So, I mean, as everything is deterministic, so what is the problem?
Yeah, I will say more. So now I'm going to artificially assume, I will remove this artificial assumption later. Indeed, I don't have a probabilistic theory, so I will have to define probabilities in the sense of typicality, that's coming later. So you're right, in fact, there is just one configuration for the universe, like you're a bit overshooting. Right now, I'm still going to assume that I don't have an initial configuration of the universe. Maybe I already have some subsystem. I made some analytic work. And these, I have really random initial conditions for the particles that are drawn according to the bound rule. I'm now artificially considering an ensemble of states. And I will write rho t of Q, the probability density. Okay, but this is, now I'm going to prove it. The probability density for Q. So again, I have randomness now in the initial condition that I'm sampling initial conditions. And so the definition, okay, this is an unfortunate choice because it's also, maybe let me call it PT of Q so that there is no confusion with the density matrix. And what it means is that if I take the average over this initial randomness, that I don't know, if you like, I don't know the initial configuration of any function of Q. Okay, now, but when I say just Q, I mean all the particle variables together. Okay, this is like a vector of vectors. Well, this is equal to the integral over Q of PT of Q, f of Q. Okay, this is the definition of the density. And now what I want is to understand how this density evolves as a function of time. And I will show that it obeys the same equation as psi squared, and so it is psi squared. How do I do that? This is a standard trick. Standard trick that I have to remember. So I differentiate this expectation value with respect to t. And I can differentiate on that side. So by definition, it's just dq, dt, pt, f of q. So that's the first way to write it. If you like, this is my star. And there is another way to write this derivative, which is to say that is to write it this way. The expectation value of d over dt of f of qt, of q of t. And this is, sorry, this is not star, actually. This is another equality, which is double star. And this is the expectation value, the average, sorry, average over initial randomness of dq of sum over k, dq k over dt Okay? But this is just another function of Q. So this I can replace by the integral form dq. This term here becomes v psi k of q. Okay, there is a sum over case that I take out. Gradient k f. And this I can finally integrate by part here. Now I'm getting a bit more sketchy with the notation. Okay, these are my two sides, and so now, okay, sorry, this was supposed to be PT. And this, so we have that star equals star star for all f. So what's inside the integral is equal. And so we have that dt pt and this is the same. So you see that rho verifies the same equation as psi square. P sorry, has the same dynamics as psi square. And so if P of 0 equals psi square of 0, then they are always equal. Then they remain equal. So this is called equivariance, this property. And this is the only, I think one can show this is the Bohm rule is the only distribution that is equivariant for these dynamics. Okay, so if we assume that we throw the Bohmian positions randomly according to the Bohm rule initially, then we only get the Bohm rule, we get the Bohm rule forever, okay, about their distribution. Their flow is right. But now we come to Mazar's question that indeed we are in a deterministic world in Bohmian mechanics. There is only one initial position for all the particles in the universe. And so there is not even any probability in the first place. So it's hard to justify the Bohm rule this way. It's at least insufficient. And the other argument is typicality. Unfortunately, typicality is not a purely mathematical argument. Okay. And so I think in the context of Bohmian mechanics, it was really explained and defended well and made precise by Detlef Dürr, Shelley Goldstein, and Nino Zanghi. And so, in fact, this problem of typicality is also the same in statistical mechanics. How do you explain randomness from a deterministic theory? So actually, we get statistics in our universe, even in the deterministic universe, by repeating experiments on different subsystems. We have a subsystem of the world, we do an experiment. and we redo kind of the same experiment, we redo it again, and we accumulate statistics. Actually, all of these points are deterministic, but overall, since they kind of hit randomly, we are going to get randomness. So now I'm going to make a very, very idealized assumption of how it is to repeat an experiment in Bohmian mechanics. And this can all be made much sharper, okay? This is because I don't know how to make better in a small amount of time. You can check the book by Detlef Dürr, for example, where they do it much better. But you assume your universal wave function can be factorized this way. And this corresponds to your n experiments. And it's really what it means to have n independent experiments where you prepare the same initial state. Okay. And now what you do is you assume that Q at time 0, which is equal, let's not put this arrow, which is Q1, Qn, assume is typical of the Bohm rule. What I mean is that, let's say we pick the initial condition of this tiny toy universe according to the Bohm rule. So what I mean, I have one sample. I'm just asking that it's typical in the sense that I don't hit something that's crazy improbable, or that would be Lebesgue measure 0 when n becomes large, for example. Okay? But then this is actually quite intuitive to see that by the law of large numbers, if you compute empirical averages of Q, okay, these Q1, Qn now for us are different realizations. And so if we want to compute, for example, the empirical average, I don't know how to write it with a hat, maybe, of a certain function of Q, well, this is 1 over n in our experimental, in our tiny experiment, sum over k, f of qk. But each individual was sampled according to the Bohm rule, and so by the law of large number, it's going to converge to the average value, which is f of q. So this is really when n is large. F of q, small psi squared of q. Okay, so if I have just one sample, this is a sort of trivial argument. Okay, if I just have one sample, then things are going to behave like the full distribution, if I have many copies of the distribution. Okay. So this is how you should understand typicality, like statistics in a deterministic world. And this is just true at the initial time, but thanks to equivalence, this is true at all time. So then, at all time, we are going to get probabilities according to the Bohm rule. And for that, we just need that the initial condition of the universe was sampled for something typical with respect to the Bohm rule.
So in the double slit experiments with this pilot stuff, it means that when I repeat my experiment, my little droplet is sampling from the Gaussian from shot to shot. What I measure is where it landed, and this depended.
Okay, maybe not the droplet. Let's take just the actual. Okay, where I send electrons. I'm just saying, in fact, when you do these interference experiments, it's a new electron every time.
Yeah.
So it's a new psi in this. So each of those is deterministic, was fixed from the early days of the universe. But effectively, you get statistics because all of these were chosen sort of initially independently and according to the Bohm.
The statement on the randomness of the initial condition.
It's still a problem of randomness of initial conditions. What I'm saying is I don't need to assume that I have an ensemble of initial conditions. What I wanted to say is that I just need one initial condition, and I can explain why experiments look random by, or why effectively I recover the Bohm rule.
But why, I mean, I don't understand why, can't we assume that we always actually prepare really, I mean, let's assume
No,
that we have
okay,
a way to prepare the good
good point, good point. So what you see is that if we pick an initial condition of the universe according to the Bohm rule that is typical with respect to the Bohm rule, then equivariance forces the distribution of the particle in the universe to be also distributed forever according to the Bohm rule, okay, because of equivariance. So there is nothing you can do to ever disturb that empirically. So there is nothing you can ever do experimentally to know particles better than the Bohm rule. Okay, so it's at the same time explaining how the Bohm rule emerges and how it cannot be. You can never get closer than the knowledge you have from the Bohm rule.
So when I'm re-preparing my cave experiment,
Yeah.
the universe is reconfigured again according to the Bohm rule, and so my initial condition of this cave experiment is again sampling some initial condition according to the Bohm rule. Is this correct?
It just needs that the initial condition is that was typical with respect to the Bohm rule. Okay, the problem is that I'm just writing a piece of the wave function here. In fact, the wave function contains the rest of the universe, and this also creates its own randomness. But
so the fact that somehow the measurements, even if we start some experiment always at the same place, give us some random result at some later time, is because perhaps this is a subset of
yeah, but this is really this argument. So when you prepare a system practically, what you prepare is a certain reduced wave function, okay, because you don't control the wave function of the universe, but effectively you have a reduced wave function. And this wave function you can prepare as much as precisely as you can, but you have no control over the distribution of the initial particle dynamics, and by equivariance they are necessarily distributed according to the Bohm rule. Of course, what we could assume is that the universe started in something very atypical with respect to the Bohm rule, and then we would have, in principle, possible Bohm rule violations. Okay, but this is, as long as you are in so-called quantum equilibrium, that is, if you are at some point typical with respect to the Bohm rule, and again, you just need to be typical as far as the whole universe is concerned, this is enough to mean that the Bohm rule is true everywhere.
But what is the origin of the universe then? What is the initial Bohm rule?
Okay, well, the initial condition of the universe, I'm just assuming, is a typical realization of the Bohm rule. So I'm not even assuming like the full probabilistic. But you're right. There is an assumption here. In the same way, we assume that the universe is initially in a low entropy state or things like that. There are this, as far as I understand, cannot be eliminated completely. But I think in this theory, the price is not very high. Like equivariance and this typicality argument make it fairly natural. Like it's not forced. At least if you have a difficulty with this, you have one as much for statistical mechanics.
Is it true that the early hidden variable models were going this way, to try to assign the randomness to the measurement apparatus, initial conditions, and this type of thing? So it's the same type of thing. Before they knew Bell. Of course, after knowing Bell, it's...
Yeah, I mean, here, what we will see maybe later, I mean, the only thing that's real are the particle positions. And for example, what people were doing initially was assuming that operators were well defined and that they were revealed maybe by the measurement apparatus. In Bohmian mechanics, no operator is well defined. Like all the measurement of something that's not position is contextual and it's sort of made up by the measurements. I will come to this in a second.
But it should be defined by the initial conditions of the universe, no?
Yeah, if you like. All measurement results are in a way computable from the initial conditions of the universe.
So that's what people were doing in hidden variable models, and then they got confused when they saw Bell.
Yeah, but Bell's theorem doesn't forbid this, of course. We'll see why. Yeah.
I mean, but at some point it feels like you need to have, I mean, how from a completely deterministic model, I mean, you somehow include this Bohm rule at some point in your time, somehow. Some non-deterministic notion, basically. You inject it in your deterministic model, and it enables you to give to get always non-deterministic results later on. But But you need. It seems like you need to complete your deterministic model with some non-deterministicity.
But it's true for all theories. So I'm just saying I don't know the initial condition of the universe, and I have to assume. The question is, what's my prior about it?
But I mean, the collapse model, your non-deterministicity
Is explicit. Yeah.
Is explicit. Is in their model.
Here it's just in the initial conditions. Yeah.
You are making a price to make it deterministic, but somehow you're injecting as the initial condition and
Yeah.
deterministic.
Yeah, that's true. That's, for example, what you're saying is one of the reasons Nicolas Jean doesn't like these models, because he thinks randomness is better revealed than put in the past. These are philosophical positions then. I personally like the fact that in this model there is no fundamental randomness whatsoever. All the randomness there is epistemic randomness, is that we cannot know perfectly the initial conditions. And we even understand why we cannot know them. So there is a sort of ultimate limit to knowledge, but still everything, all the cogwheels of the universe are deterministic. Just beings living in this universe and made of this universe can never access more. I think that's a very nice explanation of randomness. I'm not saying it's necessarily the correct one, but it's a completely alternative explanation from the usual one. And the fact that it's consistent is remarkable. I think that.
But is this consistent with the thought experiments, where in the double slit experiment you measure the momentum of the particle to try and localize it, and this would erase interference patterns?
Bohmian mechanics is consistent with all experiments of that type. There is a theorems by Dürr, Goldstein, Zangi that you recover all Copenhagen formalism. So what can be the case is that this experiment is very unnatural in the sense that when you're measuring momentum in Bohmian mechanics, you are not measuring the derivative of Q. It's just you have an apparatus that has a needle going to a certain momentum, but there is no correlate of this in the trajectory of the particle. That's typically what's going to happen. The only thing that Bohmian mechanics is going to allow you to recover are typically macroscopic objects like chairs are going to have all their particles roughly there and moving a little bit. So you're going to recover a picture of the world, at least at our macro scale, that's coherent. And weird stuff is going to happen at the microscopic scale. In a way, you have to. I mean, quantum mechanics is weird, and so the Bohmian trajectories cannot look classical or at the micro scale. Otherwise, it would not explain the weird stuff. So as you dig in, Bohmian trajectories look very weird, and if you zoom out and you have sufficiently macroscopic bodies, the Bohmian positions, one can show they really follow classical trajectories. But that's only true for macroscopic bodies where sort of interference effects decay. Well, yeah, no?
I don't want to disturb too much, but going on the question about randomness, when you do Bell's experiment, you say we choose randomly which basis we measure.
Yeah.
So do you allow this type of randomness, or is this also fixed?
Okay, this is again, in all deterministic theories, you have emergent notions of free choice. And that's fine. That's not in contradiction with determinism.
Because then you don't need non-locality, right? If you can just assume that everything is in the past, you are in
No,
the
no,
past.
no, but there is a difference between like superdeterminism and determinism. Like here, this is compatible with determinism. So we'll see that the way Bohmian mechanics violates Bell's theorem is by being non-local. So that's explicitly non-local. Actually, I erased, but the velocity field depends on the position of all the particles potentially far away. So if they probe a different part of the wave function that moves on your side, so this is massively non-local. And we'll see concretely how it manifests itself. So there is a way also, I wanted to talk about it later, to convert Bohmian mechanics into a superdeterministic theory just for the fun, like to kind of illustrate different interpretations. But at least standardly, it's a standard deterministic interpretation, not superdeterministic. It's compatible with emergent notions of free choice, but it's non-local. Okay, let me keep on and talk about measurements. And before talking about measurement, measurements. So I want to circle back to the measurement problem, because here we have particles, they move. What does it tell us? I think at the very first lecture I said, Bell told us that measurement is a theory-laden business. It's complicated to know what we can measure. We should simulate really measurement apparatus. And here we just have positions, but maybe the position of the electron in Bohmian mechanics doesn't behave at all like what we measure of it. So,
I'm sorry,
yeah.
I wanted to, so I feel like in the previous case of the collapse models,
Yeah.
these constants,
Yeah.
nature basically that you had to add.
Yeah.
And so here, I guess this constants should be replaced by somehow the initial distribution of the work, somehow,
Yeah.
probability distribution of the particles. So it seems like you need to pay still a larger price, no?
No. So if what I'm saying, so if for all initial conditions of the universe that are typical with respect to the Bohm rule,
But for this Bohm rule,
this is going to be exactly Bohm Copenhagen quantum mechanics.
but so what I'm saying is just that you need to know. Okay, so you say that.
So I'm saying
the only thing that you know is a psi zero of psi at time zero of the world.
and the Qs, and you have the Q, and you assume that the Qs are not too atypical. They are not in this type of measure zero space of implausible. Otherwise, you could maintain a breakdown of quantum equilibrium for a while. But these are not parameters, okay?
I feel like this psi zero of x in null plays a huge role, whereas before it doesn't. So it's no constant of nature. And,
No. So psi, the wave function of the universe at the initial, sorry?
At time zero.
At time zero always plays a big role for everything, even in standard Copenhagen. We rarely talk about it because we are focused on subsystems and blah blah. But
when you're collapsing it often, is it so important?
yeah, I mean, it's going to give maybe the average energy, for example. You need the original wave functions to be in a low entropy state. I mean, there are lots of. Okay, this is a huge problem in physics. How you understand initial conditions of things. So I fear it's a very long discussion. That's my fear, and that is a subtle discussion. And so if I answer it in 5 seconds, I will say things that I'm so disappointed about later. That so okay, let's just accept that for physical theories, fixing initial conditions is always a difficult thing. Understanding what we would accept, what we would not consider fine-tuned as initial conditions. I'd say in a reasonable sense, Bohmian mechanics doesn't require fine-tuned conditions, initial conditions. Quite to the contrary, it accepts a wide range of typical initial conditions, at least for the Qs. Okay, so let's do metaphysics again. And metaphysics, again, can seem like philosophy, but we have no measurement postulate anymore. So how do I connect my theory to the real world? How do I say, what do I measure? So the world is made of particles. Okay, so there are versions where you also consider the wave function to be part of the world. I prefer to see the wave function as a law, but this is subjective. It doesn't matter, okay? The world is made of particles. The particles are really important to define outcomes. And a measurement result, this is equal to a macro configuration of a pointer, of an apparatus, of a pointer. So what I mean by that is really that you should imagine that, again, like before, you have your pointer made of particles. Actually, this is 10 to the 20 particles or even more. So, and this is also made of particles. And when the Bohmian particles are in this configuration, this is a certain result. And when they are in this other configuration, this is another result. Okay, that can seem kind of crazy to be as explicit, but now we have no measurement postulate. So if we want to derive, and in principle, what you should do is solve the Schrödinger equation, solve the guiding law, and then you would see that the particles distribute either like this or like this, depending on the initial condition of the particle. Then you compute statistics, and you would recover the Born rule. That's in principle, okay? Then later we have theorems by Dürr, Goldstein, and Zanghi telling us we don't have to do that and that we can rely on Copenhagen. But logically, this is where it comes from. And all measurements, I said all measurements are like that. So this is sort of, I'm just saying the same again, but all measurements are like this. And for example, spin, you know, if you have the Stern-Gerlach apparatus and, you know, in the Stern-Gerlach you send the spins and they either go up. Maybe I should have written the other one in another color. So the wave function maybe does this. The particle, the Bohmian particle Q is going to go just one way. And then there will be a detector here, and at the end, it's going to, I don't know, it's going to, how can my detector be and still be positioned? It's going to raise the flag to show that something happened. Okay, so everything, even spin that doesn't have variables in quantum mechanics, that is just a dynamical property, guides the particle one way, and then there is then this particle is correlates like interacts with this apparatus here, and there is a flag up, and now I have a macroscopic configuration like this telling me I measured spin up. Maybe something to say again is that Bohmian mechanics is highly contextual. And so the dynamics of the particles really depend on the measurement apparatus. So if I put a measurement apparatus or I don't put it, it changes the wave function. And thus it changes the trajectories. This is sometimes seen as a bad thing, but in fact quantum mechanics is heavily contextual. So if it were not the case, we wouldn't be able to reproduce quantum mechanics. Okay. Okay, so now I wanted to give an argument for why actually there is a notion of collapse in Bohmian mechanics. A notion of. This is a semi-tricky point, so I will. Are there questions maybe at this stage about the picture of the world that there is? Yeah?
Where in the equations do the particles themselves have an influence on the wave function?
They don't. The particles have influence on the trajectories of other particles, not of the wave function. You see, the velocity field is velocity field that acts on particle k is evaluated for all the particles. So this way, particle k influence particle k plus 1, for example. Even so, when I say here, this particle will have an impact on the evolution of the particles here, not on the wave function. Okay.
Then you said preparing the measurements is like preparing the waves such that the particle that is in the wave would behave in such a way. But how can we, what is the sense in preparing the wave function if we have no control of it? It looks like that there is no free will when we're just...
Yeah, but this is a problem you had in all theories and you just never wondered about it before because it was not precise enough that you could worry about it. So I will precisely explain why. So there is a notion in Bohmian mechanics of effective wave functions, of reduced wave function. That is, this wave function is the one you use in experiments, not the universal wave function. But this is the same in any interpretation of quantum mechanics. I mean, there is a wave function for the world. It evolves. What does it mean to prepare? What did it ever mean to prepare a wave function before? No? This was not clear. It's just here, it's sharp enough that you can... that these questions now make sense, and so you are more worried. And in a way, you're right. Okay, I'm happy you're worried. But this is a nice transition because I think it's. I'm not sure I fully answer what your worry is, but at least it's going in the direction of answering your worry.
But
Yeah.
just before we move on, this drawing to me is a bit misleading because if it's denoting the Q value versus time,
Yeah.
this is not happening simultaneously. Like on some shot, you get a
No, sorry. This is the wave function
Ah,
in yellow. Maybe this is wrong. This is a weird drawing.
okay.
This is the wave function is maybe something like this. Okay.
Yeah.
And one is empty.
Right. Okay.
One as the particle.
Yeah.
Okay, so we need to understand now, we wanted a theory of the world, so we have the wave function of the universe, and this is right. I mean, to talk about the whole world, we need the wave function of the universe, but we need to understand later effective collapse. So there is no fundamental collapse in Bohmian mechanics. There is only the particles and the universal wave function as if you go to the bottom of things. So let's consider a situation that the state I have written probably a million times already, which is a measurement, measure 0 plus beta 1 Now let me look at these. So these are the two measurement states, and what we would like to argue is that the wave function of the universe typically is going to have this form, except in many times for many types of experiments. What I would like to argue is that for such a state, in fact, I can consider only one side. When this is huge, I can only take one and assume it happened. So what happens? Well, these two states, now this is configuration space I'm writing. So this configuration space, it's hard to write what it is, but it's like R3 times 10 to the 23. Okay, so it's like a huge configuration space. And in it, the wave functions have support, but what we argued before is that because of decoherence, measurement 0 and measurement 1 are orthogonal. So basically, this is measure 1, and this is measurement 0. Okay? And they don't talk together, and intuitively, they will never overlap again. So this is like saying the dead and live cat never recohere. Okay? Once you've lost the coherence, they will never overlap again. The particles of the measurement apparatus, okay, we are in configuration space. So the 10 to the 23 particles are a point in configuration space. And the point is somewhere. Because the Born rule is correct in Bohmian mechanics always, the point has to be in one of these two. It cannot be elsewhere. It has to be where the wave function has support. Otherwise the Born rule would be wrong. And so maybe it's here. The only way it could jump to the other one would be if they came close again. Otherwise, it will never come back. And if you remember the velocity formula, only thing that matters is part of the wave function is the wave function evaluated at configuration points. So what that means is that this is what people call usually the empty wave. And this here, is the effective wave function. And for all the future, the dynamics only depends on the effective wave function. And so in my drawing, if this happened, all the dynamics in the future for all the particles in the universe will only ever see the wave function as if it were in state measurement 0. And so, okay, just formally, in that case, the effective wave function post-measurement is just effectively psi f measure 0. And so this guy is collapsed. Okay, and the empty wave function is the other one. And it doesn't disappear in the wave functions of the universe, just it has no relevance for future dynamics. And to me, that's an argument. The uselessness of the empty wave is an argument for the wave function to be law-like. So the wave function is like the Hamiltonian. It's an object defined everywhere. So Hamiltonian is defined in phase space, but okay. It's an analog of the Hamiltonian defined in configuration space that's only evaluated at points where the particles are. And so it behaves more like a law instead of something real. Okay, you can also think of the wave function as something real. And there is another object that is quite useful that you can define that is fairly similar, so often confused. With it is the conditional wave function. How did I write it? So in my case, it's a wave function for the system. But that you evaluate from the measurement plus system apparatus, or if you like, the wave function of the universe, for the particle position of the apparatus, the actual Bohmian positions. So these are like the Bohmian positions. Of the apparatus, for example. But you can take a conditional wave function for everything. So you take a wave function and of a many-body system, and you fix the dummy variables to the actual positions. This is the only thing that the system needs to compute its dynamics. And these guys, both are objects that effectively collapse. So both these objects effectively collapse upon measurement. And both these objects behave like the wave functions we are used to in the Copenhagen interpretation. Okay, and that's really important. The wave function of the universe never collapses. Most of its blobs and branches are never explored by the particles. But these guys behave like the wave functions you have the intuition of. This is the ones you prepare. This is the one when you consider your small systems. They are always either effective or conditional wave function. And so this was 3.2, this was 3.1, okay, this is 3.3. And this 3.3 is hard to, in fact, this is just a summary, and it's not really a section of itself, but this is Copenhagen. So I think so far, I have given a pretty good arguments from equivariance and typicalities and how measurements, then what is metaphysically there, then how we can define conditional wave functions that do collapse the way we expect. I given a convincing hint that we recover Copenhagen. It can be made well, and this is a paper by Detlef Dürr, Shelley Goldstein, and Nino Zanghi. Of 1992. Is that we recover all of quantum mechanics, of standard quantum mechanics, and including POVM. So like including, let's not put POVM, but at least including all operator measurements. Okay, as I argued in the first course, if you have all operator measurements, you also have POVMs. But there are these, when you measure something else, when you measure whatever operator, this operator you measure, say the spins in Bell-type experiments, have no real-world correlates. They are just dynamical properties. They are not ontological properties. And that's how it escapes many of the arguments by von Neumann, for example, that sort of people were really trying to put the spin values as hidden variables. And this is not what Bohmian mechanics does. Otherwise, it would be falsified. OK, this is true provided quantum Bill equilibrium is preserved. That is, you start from a typical condition, and then equivariance ensures that you keep it. So this is not true. So if you can assume that you start with a certain wave function, and that all the particles are, I don't know, on the tail of the wave function, for example, and this is non-typical, and this will not give Copenhagen. This will give violations. And some people are studying possible violations from this, but given how natural typicality is, these violations are a bit unnatural, I find. OK, I have some illustrations now. about what the theory says because it's a bit weird. So let's face the weirdness. And then I will have a few comments about exotic interpretations, and I think we will be on time.
I have maybe a question.
Yes, sir.
I mean, somehow I feel like uncertainty principle could become a little bit weird now. I mean, if you, for example, imagine this situation that you're showing over there. You measure the particle position, you see it over there. Right away you measure its momentum.
But
and then again the measurement, and then again the position, and now you see it over there.
But like in Copenhagen measurements, measurement changes the wave function. So
no,
measurement changes the effective wave
function.
function.
It very rapidly.
But like in
your particle has to go very far. Let's say that very rapidly.
It doesn't have to be. So if even if the wave function, the position is always well defined in Bohmian mechanics, but that doesn't mean measurements of positions will be sharp. When you measure the position, it doesn't necessarily reveal exactly where the particle was, your pointer. So I should have added a discussion of the uncertainty principle, but the bottom line, actually, a consequence of this is that there is no problem. At least you have to understand that if you define, there is no uncertainty principle between Q and the derivative of Q. They are both sharp. However, there is an uncertainty principle, which is the expected one between measurements of positions done this way with a macroscopic apparatus, and you look at the needle, which side it is. The same measurement of momentum. Again, measuring momentum is maybe you can do time of flight. So again, it's position measurement, or you can do other things. And then this will give the right uncertainty relations from quantum mechanics. But these are, in this picture, uncertainty relations are really dynamical things. We cannot, because of the way apparatus are coupled to the wave function, like how the Hamiltonian are coupled, we cannot extract, we cannot define two things well together. But this is not, this is, if you like, a superficial conflict, but once you work it out, there is no conflict anymore. Okay, let me still give some weird stuff, okay? Like, so I wanted to show a few illustrations. And the two illustrations I want to show are interferences and non-locality. So the first is 4.1 interferences, and where the pictures is kind of weird. Okay, so I don't want to show double slit because it's a mess. I just look at sort of a more Mach-Zehnder-like. Let me keep my color code from before. That in yellow is kind of the wave function path. So okay, I sort of have a beam splitter that's splitting my particle in two paths like this. And okay, they would interfere here, and I could also measure them far away. Okay. I guess that's the intuitive picture so far, okay?
There's another beam splitter where the crossing is?
So either you could just do a measurement here, or you could just let them go, for example, okay? Just let them cross here. I could do a beam splitter, yeah. No, but I was just even considering maybe I just measure here, but okay. That's... yeah, okay, sure. The point is, what is the particle doing? So what is a single particle doing? And you see that the particle, maybe it goes here, and there is a possible trajectory like this. But it's a, let's say I always consider the same state. I want to look at what are the possible trajectory particle positions, and certainly I have two possible positions that are going to correspond to the two results. And the question is, how does it look like? And you see that here, it cannot, because it's a first order equations, the two possible particle positions cannot cross each other. So the Bohmian particle is doing this, actually. So that's one option. And the other option is this. So they behave sort of classically, except at the strong quantum point, if you like, where you have the interference effect, where they repel each other. Of course, it's very small, okay, if you look at it. But it's always the particle that goes up that ends up, and always the particle that goes down that ends down. Of course, it's random here, so it doesn't bring problems with the usual predictions. But it's quite interesting. Like just it's sometimes they are called like surrealistic trajectories, but they just show that at the microscopic scale, when there are interferences, I mean things can behave weird. And there is an argument by several people, but by Laloé, that for large n, we have a good classical limit. This is not very well explained what I mean by large n, but sort of if you have macroscopic bodies, there are particle positions that don't do the type of stuff. They evolve like the classical trajectories we would expect. And finally, I think it's nice to see non-locality. So this is a subtle point. I'm picking an example from Diane Rice, which I took from Bricmont's book. So now you imagine that you have an entangled state that is going to be 1 over root 2 of particle 1 going past A, tensor particle B, particle 1 going past A times particle 2 going past B, and then a superposition with 1 going past A prime, tensor 2 going past B prime. Okay, again, we should, in principle, rewrite that in terms of proper wave function. Now I'm using the intuitive notation. So what I mean by that is that, yeah, I have two particles, and they are entangled in how it can. I should again maybe use this for the wave function. Like the wave packets can go like this or this, or like this, or like this. Okay, this is an entangled state, and you should imagine they are far away. So these are, if you like, there are two sources, and they are entangled in the state they generate. This is not a very physically. I mean, you could make it better. Maybe there is an entangled photon that goes here and then is splitted here, for example. And now, okay, this one we let go. So this is A prime, B prime. And this is particle 1. This is particle 2. And so what you do, okay, now I should have imagined, because I'm an idiot, I took them very close, but that they are in galaxies far, far away once they have been created. Now you put this type of mirror here, Okay. And what you see here is that I'm just wondering what is going to be the Bohmian positions, the Bohmian trajectories. Well, they are like this. So here they can cross each other because these two, and then there is also Bohmian position like this. Because of the states here, I should look at overlap of, configuration, like trajectories cannot cross themselves, but it's configuration space trajectories. So here, this guy here, they cross here in physical space, but they don't cross in configuration space. Okay, because when this guy does this, this is here, and when it does the other way, this is here, and these are not crossing points in configuration space, okay? So this, in that case, in that setup, the trajectories cross. Now I will look at the other case, where now, on the other side, I also put a mirror.
when you say the trajectories cross, I thought it like the wave function is doing something that interferes and so on, but the particle is either in one of the two branches, right?
Yeah, but here nothing prevents the actual particle from going straight.
Yeah. So on one instance of the experiment.
Yeah, sorry, I'm showing two instances. I'm showing the two possible
Yeah.
trajectories, just showing that they cross and they don't do this avoidance here, like in the other one. Now let's say I make the setup symmetric, and so now what we will see, then now they have to avoid themselves in configuration space, because I made them recombine here, so they will be at the same point, and so here the trajectories look like this. Okay, again, these are two possible trajectories, and these are also two possible trajectories. So these are the Bohmian trajectories in that case if I put mirrors here. And you understand instantly that this is non-local in the sense that the Bohmian trajectories here are massively changed by the fact that I put a mirror here. And this could be light years away. Okay? So this is a strong dynamical influence at a distance. Fortunately, because of equivariance and because the Bohm rule is preserved, this doesn't change the statistics here because I cannot prepare. So if here I could systematically prepare a particle going up, then I could use that to send signals faster than light because it would go up if Bob put the mirrors, and it would go down if Bob didn't put the mirror. But I cannot, and I'm stuck by equivariance. And so equivariance shields us from the non-locality of the dynamical laws. But clearly, if you plot the particles like individual trajectories, they are massively contextual. They depend on what type of apparatus we put. And they are also massively non-local. Okay, and that's in a way we have to live with this. And as I tried to argue before, that's unavoidable if we want to reproduce quantum mechanics. In a way, this is done in a blatant, like obviously a gross way. Okay, like we can really see the non-locality. And okay, if you want to break down equivariance, most likely you would also maybe create possibilities to signal in this type of scenarios. So okay, it gives a very clear picture of the world. As I would like to argue, as for collapse models, the relativistic extensions are not so neat. Okay, so this is a neat theory of n particles, but the relativistic extension is. Yeah.
How the comparison with the collapse model? How I feel like the collapse model, it's really kind of a the theory that you can falsify something.
Yeah.
Here it doesn't seem to be the case, right? I mean, you say it's basically strictly equivalent to the Copenhagen.
Yeah. Empirically, yeah, that's true. Yeah.
So how are they really comparable?
No, it's different. I agree. They are different. One makes different predictions from, again, the standard model at least. And one, in principle, should be totally embeddable in the standard model. But okay, advocates of Bohmian mechanics, and in a way they have a point, would say it's just a sharper version, and from which you can derive Copenhagen and then use Copenhagen. Like, if you look in the book by Detlef Dürr and Stefan Teufel, they say practically every person should essentially, at the end, use the Bohm rule. And okay, it's just now we have a sort of statistical mechanical justification of why it's reasonable, and we feel much better. Another point is that maybe later, when you want to extend the theory to new things, you are going to make an extension very different if you allow yourself to use the Bohmian positions to do whatever. Okay, you could say, now let's add an interaction between these Bohmian particles that is not mediated by the wave function or whatever. I mean, that gives you new ideas. Usually, these types of ideas tend to break everything. Okay, they will break equivariance, and so they are not good ideas. But okay, you can maybe do a little more on top. Let me close this so I would like to stop with Bohmian mechanics and do 5 last minutes about interpretations more generally, because I took these two examples because I think they are the two sharpest one. Okay, really, if there is one thing to remember, is I think these two examples are sharp, and they allow to dispel many myths about quantum mechanics. So if we say quantum mechanics, for example, implies absolute indeterminacy of properties or whatever, this is fundamental. That's something you can believe, but it's not logically implied. The simple fact that Bohmian mechanics exists, whether or not it's correct, shows that it's not a logical implication. And many things are like that, and I think that's why it's good to have these examples in mind. And it allows you to know what is really a consequence of the predictions we have and of what we see in experiments, and what is more of a choice. Okay, so this way, then you can make your choices, and your choice often is not going to be to choose these interpretations. And I think none of these two is very convincing, and that probably I'm still waiting for a better one in a way, or that would be more natural, I don't know, more naturally emergent, but still they are good examples to have in mind when you discuss foundations. So, okay, I don't know if I rewrite much, maybe I will just talk, because there are things okay, what are the other interpretations? So maybe others. I'll go fast. So you can really check Frank Laloe's book, which is do we really understand quantum mechanics? He really has a long overview. So maybe popular ones. I will distinguish popular ones from less popular ones from crazy ones. Okay, you have the many world that maybe that was a mistake, but I never really tried to define. So this is kind of, you keep the superposition and you try to make sense of the world like this, and you have difficulty recovering the Born rule. And you have lots of worlds. I mean, that's, and I think this is, if you want to get to use decoherence only and nothing else, this is what decoherence naturally leads to. Okay, and then usually proponents of decoherence, like Zurek, say that their interpretation is, not their interpretation, their formalism is interpretation independent. That's true, we use decoherence for everything. But if you want to use decoherence alone, I think it's very natural that this leads to many worlds. Okay, the proponents right now are historically Everett. David Deutsch gave him his intuition, so at least it's a strong intuition pump. And nowadays it's sharpened, like people try to make sense of it. And examples of these people are, for example, David Wallace, people trying to make sense of the many worlds. Then you have cubism, so quantum Bayesianism, which is mostly pushed by Chris Fuchs and actually Carl Kayes historically, but I think really Chris Fuchs is the one pushing it right now. It's also the interpretation of Bitball I cited at the very beginning likes best, as far as I understand. And it's all about information. So if we're being honest, they are not in principle against reality existing. It's just they don't care about reality. Okay, so they will say everything is just information. I think the problem of this view is that if you say everything is information, I answer information about what, and now I want to make my theory about the what, because I'm a physicist, okay? So I think theories of information can be, okay, then don't worry, Chris Fuchs has answers to this type of cheap argument, but I remain convinced by my cheap rebuttal that at the end it has to be information about something. And if you make a deep theory of nature, just tell me what the something is your information is about. Or at least there needs to be a notion like this. Okay? In a way, there is relational QM, quantum mechanics by Rovelli. To be fair, I don't fully understand the distinctions with QB. It's also a sort of information-based, but it's not all about information, it's all about relations. And again, you see that these interpretations are different in that they are based on words on top of the formalism. So they are really interpretations, whereas what we have shown, what we have discussed today are more reconstructions, like mathematically sharp, if not appealing, reconstruction of the formalism. Okay, and then you have various neo-Copenhagen. Okay, but this at least is in our same framework of something realist, trying to give a picture of the world. These types of interpretations have a different objective, okay? And they will justify why they have a different objective. There are some programs to try to construct realist interpretations There are programs for realist interpretations. Some of them are just different collapse models or different versions of Bohmian mechanics. Let me not consider those, okay? You understand that I showed examples, but you can infinitely refine those. Like, I want to show some programs that are different, fully different. There is one idea, which is to trade non-locality. So the non-locality we have in theories like in Bohm, or actually collapse, for an all-at-once theory. This choice is sometimes called retrocausal, but I don't like it. So there the idea is, okay, the theory is non-local, but maybe instead of seeing the fundamental laws of nature as a Cauchy problem, where we evolve things on hypersurface, the laws of the universe are prescribed all at once, and there is a global consistency condition. And this means there is some form of retrocausality, which makes it very weird, like the future influencing the past. I think a much more natural way is to see it as an all-at-once theory. And initially, Leibniz's formulation of mechanics was an all-at-once theory. You have a least action principle. It turns out that if the action is a local integral of a Lagrangian, then this gives back a Cauchy problem. So you can evolve forward in time. But so you should imagine something that's maybe a double integral, okay, in time, with some time dependence. This would not be reducible to a Cauchy problem. And that could be a way to evade the no-go theorems while keeping some form of locality, maybe, but yeah, with backward causal interactions. So this is something that, but it's more of a program that I find superficially seducing, but it's not instantiated at the level of precision of these interpretations. Okay, then there is the trace dynamics of Steve Adler. And in this version, there is just no space-time. So no space, like rather maybe no space. All the interactions are all-to-all in the universe, and then geometry is emergent. And then if geometry is emergent, you understand how some notion of locality can be evaluated, okay? Because there was no locality in the first place. Locality was just emergent. And then you have the cellular automata interpretation. Okay, Wolfram, I don't understand. But okay, I was thinking more of Toft. And in this cellular automaton interpretation, so what Toft claims is that, so these are supposedly local, so it's supposed to be superdeterminism that explains Bell's theorem. But the problem is that these models are sort of not very well instantiated to discuss a Bell-type situation, okay? Like there are too much of toy models to deal with a concrete Bell scenario and understand what the hell is going on. I think that's why people are skeptical that it works, but okay, Toft is a very smart person, and so maybe he's onto something, but I don't understand these, okay? And so I would have liked, ultimately, I would have liked to give more interpretations or more ways to see the world, and I think if you want to make it sharp, there aren't that many, or there are equivalence classes that are of the type of collapse or of the type of Bohm, or maybe of the type many world. I finish with the crazy one because I think it's good, and especially if we go for a drink later, the crazy interpretation. There is Bell's many world. So it's Bell is not taking it seriously, okay? This is an illustration. So at each time t, so it's a bit like Bohmian mechanics, but different in a very important way. At each time t, you pick q of t randomly with the bound rule. For psi of the universe, okay? Okay, what happens in this world? So what is crazy, and this is to show, this is a nice illustration of the Duhem quinthesis, so that you can have absolutely crazy ontological, metaphysical explanations that are compatible with what we see. So in this world, so the wave function of the universe has many branches. Most of them are totally unrelated to our world, okay? Because back in the days, measurement-like situations split the reality in various things, okay? But at each time, you drop a configuration in configuration space according to the Bohm rule for the whole universe. So, boom, this situation where we're in this classroom appears for an instant. The next instant, it's replaced by another random sample from this wave function, okay? That is completely different. Maybe a world in which the Earth doesn't exist. And maybe, in a lot of time, some configuration that is not so dissimilar from this one will be sampled again. Every time, all the beings that come into existence have the memory of everything that happened before, so they see no contradiction with the world, okay? And so this is completely crazy. Okay, no one believes in it, but it's a nice illustration of it's hard to falsify this, okay? It's hard to falsify this. So everything we see, philosophers discard this by saying there is no science possible if this is true. Like we can, but in principle, this is one of the crazy interpretations that is possible. I think I will conclude this crazy. I have other crazy that I can discuss later, but they are. This is the craziest. This is the nicest crazy one. Think about it, okay? That this could be the reality of our world, and if so, everything you thought you knew is a lie. And right now you're thinking, no, it's not possible because I just lived the instant before, but that's a lie again. Okay, and the open end of all that stuff. Why? So you see that the problem with foundations of quantum mechanics is not that there are no solutions realist where there is a tangible world, is that there are too many, in a way, at this level. There are 50 shades of Bohm, 50 shades of collapse models. The problem is that we can't decide. And the problem is that all of these constructions are not relativistic, and that so far there is not a convincing one. And so at the beginning, I said that we would simplify the problem, that we would try to make sense of quantum mechanics and foundations by going to n-particle systems instead of full quantum field theory, because it's too hard, and that this was an important first step, at least see if we could make sense of n-particle systems. This, I think, they are examples. We are confident this is a reasonable, this is understood. Maybe none of these answers are right, but at least there is various options. Now we need to do precisely what I said we shouldn't do at the beginning pedagogically. We should attack the relativistic case. So go to quantum field theory and see if it selects some interpretations or see if it helps. Ultimately, we don't need an interpretation of quantum mechanics that works for all quantum mechanical theories. We need one that works for the ones that are instantiated in the world. So for example, there might exist interpretations or reconstructions that work only for the standard model and not for anything else. If so, that would be amazing. That would be even better because it would single out the standard model as special. Okay, so we don't know, but that's the next frontier. The other frontier is gravity also. So basically, anything where there is more than non-relativistic quantum mechanics will give us constraints or maybe hints about how to proceed. And I think that's where the field should go. Okay, now that you know the field, that's where you can make progress, I think. Okay, I think that's over. Thank you very much.